This video is about simplifying radicals with variables. In a previous video we talked about how to simplify a radical without variables, meaning if we have some kind of integer and we take the square root of it, what's another way, a simpler way to write that square root? We're going to basically be doing the same thing here. So we're going to start out with a numerical example just to illustrate what we're talking about here, and then we're going to start working with variables. So let's start with 2 to the 9th power. 2 to the 9th power is 512, and I'm basically taking the square root of that, and we're going to expand this out. We don't necessarily need to in order to do this problem, but just to illustrate what's actually going on behind the scenes, we're going to use an explicit example. So if I take the square root of 512, if I try to evaluate that, it's not going to be a perfect square, and therefore it's going to be irrational. So I'm going to find a better way to do this. I want to find a different way to represent the square root of 512, so I look at what I can pull out. I notice that it ends in a 12. That means that the entire number, since 12 is divisible by 4, the entire number is divisible by 4. I know this because of my divisibility rules, so you might want to go back and review that if you need a little bit, if you don't remember all of them. So we're going to have 4, and again, we are pulling out a perfect square, and then we just write the leftover right next to it. So this is just along for the ride. This 128 is just along for the ride. What we are really after is this square root of 4. So this square root of 4 times square root of 128. And I get 2 times the square root of 128. And I notice that, again, that this ends in a 28, so I know it's divisible by 4 again. So I'm going to copy that too. So every single time I'm bringing down the coefficient that I had before. So I'm going to write square root of 4 times 32. And then I'm going to split this up just like I've been doing. Square root of 32. And then that's going to be 2 times 2 times the square root of 32. And then I have 2 times 2 times square root of, I know this is divisible by 4 again. And I know I could pull out an 8 here, but I just want to illustrate something. Or not, but rather a 16. I could pull out a 16 instead. But I just want to illustrate a point here. 4 times square root of 8. 2 times 2 times 2 times square root of 8. And then that'll be 2 times 2 times 2 times square root of 4 times 2. And that'll be 2 times 2 times 2 times square root of 4 times square root of 2. And then 2 times 2 times 2 times 2 times square root of 2. Now, instead of writing this as 16, I'm just going to write this as 2 to the 4 times the square root of 2. Now I'm going to see a pattern. If I tried this with if I tried this with a different number to start out with, if I did this with 3 to the 9th power and took the square root of that, I would get something very similar. If I had 3 to the 9th power and took the square root of that, if I did that same process, I'm not going to go all the way back through that again, but what I would get is 3 to the 4th power times the square root of 3. If I had 4, let's skip 4 because 4 actually simplifies a little bit better, but 5 to the 9th power, and I take the square root of that, that should give me 5 to the 4th power times the square root of 5. If I tried doing this over and over again, I would start to see a pattern emerge. So let's see if we can untangle what all of these look like. And we have a pretty good idea for what it's supposed to look like here at the end. If I take the square root of x to the 9th power, that should equal x to the 4th times the square root of x. Let's see if we can actually derive that. So let's go over here and do another problem. Let's simplify x to the 9th power. I'm going to do this the long way first, and then I'm going to show a shorter way of doing this. So x to the 9th power, that's the same thing as x to the 2nd power. I'm just pulling out a perfect square. I know that x to the 2nd power is a perfect square. And then I multiply by the leftover. My leftover here is x to the 7th power. I know because of the rules of exponents that 7 plus 2 is 9, and therefore x to the 9th power is the same thing as x to the 2 times x to the 7th. I'm just taking the square root of both of those. I'm going to split this up, just like always. Square root is x to the 7th. This will be x times square root of x to the 7th. And this will be x times, and again I'm going to pull out another perfect square. I know that this is x squared times x to the 5th power. Again, I can confirm that x squared times x to the 5th is x to the 7th, so I'm not really changing anything. I'm just changing the way it looks. I'm not actually changing the number itself. And I'm going to multiply that times square root of x squared times square root of x to the 5th. That will be x times square root of x to the 5th. I'm going to do that again. And if you know what I'm doing, and if you know where I'm going with this, then you can just skip ahead a little bit. X times square root of x squared times square root of x to the 3rd power. X times x times square root of x to the 3rd power. And then this will be x times square root of x squared times x to the 1st power, or just x. Let me write this 1 up here for emphasis. It's not necessary, but I can write it. And I get that's equal to x times square root of x squared times square root of x. That's equal to x times times the square root of x, and that will give me x to the 4th power times the square root of x. And again, I started with x to the 9th power with a square root around it. Now, if you notice, if you watch that entire derivation of this, you'll notice that the process that I went through is exactly the same as the process I went through over here. I didn't really change any particular step. It took me the same number of steps to get here, to get to x to the 2 to the 4th power times square root of 2, as it did for me to get over here. So let's see if there's a shorter way that I could do this. Square root of 2 to the 9th power. I could see that this is the same thing as 2 to the 4th power times 2 to the 4th power. If I add these two together, I get 2 to the 8th power, so I need to have another 2 here. So all I did was I wrote this differently. And just to verify, I can show that 2 to the 4th power times 2 to the 4th power is 2 to the 8th power, times 2 is 2 to the 9th power. So I know that these are indeed equal to each other. Now what I'm going to do is I'm going to notice that this is actually 2 to the 4th squared. So I can write this as 2 to the 4th times 2 to the 4th. And then I'm going to separate out that square, and I'm going to basically pull out 2 to the 4th power. I should rewrite this. 2 to the 4th power right here times the square root of 2. So what I'm actually doing is I'm noticing that, again, we talked about this in class, this is actually 2 to the 9th to the 1/2 power. When I raise a base to a power and raise that entire thing to another power, all I'm doing is I'm multiplying my exponents. This is 9 to the 4.5 power. Oh, I'm sorry, 2 to the 4.5 power. And then that's the same thing as 2 to the 4th times 2 to the 1/2 power. I can verify that these things are actually equal by working the opposite direction. If I work upward, 2 to the 4th power times 2 to the 1/2 power. I would just add the exponents and I get 2 to the 1/4 power. I'm just working in reverse. So instead of going upward, I'm going downward. And then I would get, that's equal to 2 to the 4th power. And again, this is just another way, this guy right here is just another way of writing the square root. Remember that to the 1/2 power is a square root, and I have a 2. So this is just 2 to the 4th power times the square root of 2. If I go over here and do this again with the x to the 9th power, take the square root. What I'm not doing, and let me do this in another color. What I'm not doing is I'm not doing x to the square root of 9. This is something completely different. What I'm doing instead is square root of x to the 9th power. That's equal to the square root of x to the 4th power times x to the 4th power, and then times square root of x. If I multiply x to the 4th and x to the 4th, I get x to the 8th. If I multiply that by x to the 1st power, I get x to the 9th. So this does check out. This is x to the 4th power times the square root of x. Again, another way that I could look at it is that the square root of x to the 9th power is the same thing as the 1/2 power of x to the 9th power. When I simplify that, I get x to the 4.5 power. That's x to the 4th power times x to the 1/2 power, and I get that this is equal to x to the 4th times the square root of x. I'm just transferring this x to the 1/2 power into this square root symbol right here. So here's the punchline of what I'm doing, and this sometimes it's easier to see with a more complicated example. If I have x to the x to the 101st power, and I take the square root of this, all I have to do is take half of 101. So half of 101 is 50. But I've got a remainder. My remainder, when I divide this by 2, is 1. So I have the square root of x to the 1st power. Something similar happens if I do the cube root of x to the 101 power. If I divide 101 by 3, I get 33 and then some odd cents, but my remainder is 2. 33 times 3 is 99, so I would have a remainder of 2. So this will be the square root of x to the 2nd power. Whatever my remainder is, that stays inside of the radical. If I had to do this with the 4th power, x to the 101 power, or sorry, the 4th root of x to the 101 power, I would take this 101, divide it by 4, and I would get x to the 25, and then on the inside I would have x to the 1st power. That's my remainder.